Merhaba. Hi. Okay, so can you hear me?
Yes.
Okay. Do you also see the slides? Sorry.
Yes.
Okay, good. So we can start. We were talking about this block IDX and thread IDX business. It may be confusing at the beginning, but one-dimensional, well, it is really easy. As I told you, the question was, could you explain a little bit more multi-dimensional thread part? Yeah, why not? So let's start with this. Let me switch to English. So this is number of blocks. I mean, we do this in fact. So number of blocks, number of threads per block maybe. So if everything is one-dimensional, what we do is simply this, right? So this is number of threads. And then once you run it again, so there is nothing changing as you see. So we have 64 threads again. So to play with the numbers, let's do this. Let's have again 64 threads, but this time we have 4 blocks. So block 1, block 2, or 0, 1, 2, 3, and each of them contains 16 values. Why not? So if you check it now, the values will change. As you see, block 0, it contains 16 threads. Block 1, it contains 16 threads, and the global thread IDs are increasing based on their first block IDs, and after that thread ID XX values. So let's do something like that. We can in fact do this dim3 and dim3. So this is the struct that I was talking about. I mean, this should compile. Now, in fact, this creates a 3-integer coordinate, three-dimensional coordinate, dim3, where the first one is 4, the others are 1. And this is what I was saying always. So this is the default, which is 1, okay? And this again, 16, 1, 1. So this is equal to this kind of fact. So for 1, 1, 16, 1. So I am creating a grid. I see the output is the same as you see, 64 threads, 4 blocks. So the output is the same, and I'm creating a grid of dimensions 4 by 1 by 1. So there are 4 blocks inside, and the number of threads per block, which is again, so this is not number of threads in fact. So this is, let's say, grid, and this is block. So this is what we are doing in fact. So we have this grid and this block. Let me see. Okay, nothing is wrong. So what if we do this 2 by 2? So let's see the output. So we have 2 by 2 grid. So again, 4 blocks, but 2 by 2 this time. So 2 here, 2 here. And inside each of them, I have a one-dimensional thread structure, okay? So again, I will have 64 threads in total, but this thing will not work now. In fact, just to be... So maybe it's better if we do this. And then this will be again global thread ID. But now I want to also print these things. So block IDXY. I'm printing the block coordinates here. Okay. For each block, I am printing for each thread, I am printing the coordinates of the block. And I want to do the same for the thread. Thread IDXX. Z, Y, and do this. Okay, so let's see the output. Okay, so as you see now, I have, okay, so this is the block 000, where is it here? And this is thread 000 inside that block. I have one-dimensional block, so threads are organized 1 to 0 to 15. As you see, the others are 0. But that's this thing, okay? And when you go, okay, so the global thread IDs, now it doesn't work because we didn't take the block dimensions into account. So we only take this thing into account, okay? So how do we compute the global thread ID? I want the values again go from 0 to 63, so 64 threads. So one thing that you need to consider is this. So I mean, the logic is really simple. You first want to find the global thread ID of the first block, first thread, global thread ID of the first thread inside the block. Okay, so after that, by adding your local thread ID on top of it, we have a local thread ID addable because we have a one-dimensional block. So you can find your global thread ID, and to do that, you first need to know the number of threads inside each block, right? So how can you compute that? Well, this is simple. Maybe block in X times block in Y will give me that, right? So this is, I have 16. I can also add this just to be sure. This is 1, X still is 2R1, as you see. But okay, so this is the number of threads inside the block. Since I have a two-dimensional grid, so let's consider how do we do that? I need to multiply this with my block ID. So if I multiply the number of threads inside the block, which is block in X times block in Y times block in Z, with my block ID, I find the global thread ID of the first thread in my block. So what's my block ID then? Let's find it. So this is a two-dimensional grid. So I need to first multiply this with grid X, right? So this is a square, in fact, or it can be rectangle. But what I do is, so to find the ID of this guy in a two-dimensional grid, yes, I first need to multiply the Y value of my block ID XY, that coordinate with the number of blocks at each row of the grid, which is grid dim X, to find the ID of the first block in my row. And I can add block ID X to that. So this will give me this will give the block ID for me. Okay. And if I do this, and as you see, the values are again from 0 to, let me see, 0 to 64. And for the first block here, as you see, 0, 0, 0, block 0, 0, 0, the values are from 0 to 16. And after that, for 1, 0, 0, it is 16 to 32. For 0, 1, is it here? It is 32 to 47, and etc. So, what can we do more? I can do this. So let's add this. Okay. So I changed the block structure this time. Grid structure is the same. So that part in the logic, so remember that what we do is we find the global thread ID of the first thread in my block, which it doesn't change with this modification because the grid structure is the same. The number of threads inside each block is the same, but I need to add something on top of it. And that thing is now my thread ID XX. Okay, so I need to do the same thing that I did here, in fact. So this thing, which finds the ID of something like thread, like block in a two-dimensional block or grid. So it can be applied here, right? So I can easily say thread ID X, Y times block. If you do this, as you see, the things are the same again, but this time thread coordinates are two-dimensional. So the values are again from 0 to 64, and for the first block, they go from 0 to 15, sorry. Yeah, for the first block, 0 to 15. And the last thread is thread 33. The first thread is thread 00, etc., etc. Okay, so this is a multi-dimensional extension of what we have learned. There's a question. How can we match the coding block thread geometry with our physical GPU device? These are all abstract. So we will learn that blocks are scheduled on top of the streaming multiprocessors, which we call as GPU processing unit, GPU core, in fact. And there is no wrong geometry or right geometry. These things are abstractions, okay? Warp is scheduled on top of a 32 core architecture, 32 core region, which is where all these cores are controlled by the same controller, but the rest is abstract. So you have blocks. Blocks are assigned to the streaming multiprocessors in a round-robin fashion, and there is nothing wrong and nothing right on that. These coordinates, these abstractions make you more comfortable when you are working with volumetric or two-dimensional data, as I told you. For matrices, matrix multiplications, they are useful. For the Gaussian process, they are useful to understand how a molecule is distributed, diffused, okay, in a three-dimensional spaces. So for these kind of things, these are really useful because you will know that by just getting the thread coordinates and block coordinates, you know which region are you working on, okay, in a 3D volumetric data. So this is really useful for these kind of applications. For one-dimensional things, if we can go simple again, and you can just say either integer or dim3 and give a single number here and single number here, which will correspond to the number of blocks inside your grid or number of threads inside your block. Okay. Okay, so let's continue. We will be done with this slide set very soon. Okay. So CUDA toolkit, compiler flags, debuggers, profilers. So this will be the content for the next slide, but I will skip most of the content. I will just show you one or two things. Why? Because tomorrow that will be a course on these things. But we need MVCC to compile something, so we need to learn it anyhow. So MVCC is the CUDA C compiler. As I told you, we have device code and host code in the same file. For instance, here I have one device function, sorry, host function and one device function here. So there's a kernel that's executed on the GPU, and this is some function, main function is executed on the CPU, right? So the MVCC compiles the device code and then forwards code on the host compiler. So G++ is running on the backend still. And it can be used, MVCC can be used to compile and link host-only applications. It's also possible because it will be forwarded to the G++ anyhow, okay. Let me do this again. Okay, so this is the hello world example, and we already covered that. So we compiled it out, and we added this kernel here, and we run it with multiple things now. So one thing you need to be careful about is, I told you that this thing can run, this thing can compile all the code, right? If you, for instance, let's copy the code that we have written to main as main.c or main.cc. Yeah, that's possible. So if you do this, for instance, it will give you an error, okay? It says no such file or directory, but if you compile main.cu, then it compiles, so there is a reason for that. MVCC only parses Q files for CUDA, so you need to have Q extension in your file, or you can treat all input files as Q files by passing that parameter. So you need to be careful about that. We already did this. Yeah, there are many profilers, many compiler flags. So let's talk about this a little bit. So there are two compilers being used. MVCC compiles the device code. Host compiler is still the CC++ compiler that you use to compile CC++ code. MVCC supports some host compiler flags. I mean, since you are using the host compiler, you may want to pass parameters to that, right? And the X compiler, this thing, forwards the parameters to the host compiler. So when you say minus X compiler minus fopenmp, it means that the host code will be compiled by using that parameter. There are debugging flags. This is similar to the GCC, minus G, minus capital G. Minus G includes host debugging symbols. Minus capital G include device debugging symbols. And this include line information with symbols, which is really useful, especially if you are trying to find an invalid memory access. So CUDA memcheck. So that is the thing that I want to talk a little bit. And after that, I will be, I think, done with this. So, because as I told you, tomorrow that will be the course. Okay. So you can, by the way, do this to see what's happening with the GPU, which functions are called, which kernels are called, how many times, how much time did every one of them, each of them takes, not each, but okay, there is average, minimum, maximum values for each. So we called the kernel only once, and it took that much time. And that is also for this one, there is nothing exacting because we only covered the GPU thread IDX business, block IDX business. But let's go to here. And let's start with this one. Let's see what's here. Okay. Okay. So let's try to understand what does it do. And we have learned everything here, in fact. Okay, so let me also put that here. So I have a macro here, and that macro is important, especially for the beginners. And I suggest you to use it as much as possible. So here, what it does is we solve that function CUDA get last error, and we store it somewhere. It resets the last error as CUDA success, but we already stored the value, so it doesn't change. It doesn't mean something for us. So we check the last error. If it is CUDA success, then okay, we continue. Otherwise, we print where the error is coming from, what's happening, etc., right? And this global kernel. Okay, so that is again a kernel. We will talk about this global. But that is now, you know that from the previous kernel, you know that is something we call from the host, okay, on the device. So there's a kernel, we call it from the host, or there's a global, and it gets two parameters, one pointer, so there's one array and one size, I think integer n. And you now are familiar with this thing. So everything is one-dimensional, right? Let's check. N is equal to this, threads is equal to 128, and blocks. So this is syntactic sugar, okay? So I have that many elements, and I want to set some value for each element, okay, for each element. And I want to do this on the GPU. How many threads do I need? And I want to put that number of threads inside my block, okay? How many blocks do I need? And the next question, I know that how many threads will be in my block, and I will need the answer of this question. How many blocks do I need? So if you add the number of threads inside the block -1 to the number of elements that you have, and divide it to the number of threads that you have, then you will reach the number of blocks that you need. Or you can use the ceil function, in fact. That's also another thing that you could do. So in here, let's print it, in fact. So you will have that many blocks, and that will trace this will print one. So anyhow, okay. So you started. You have the you have one pointer, and after that you have that CUDA malloc manage. You already know what it does. It is the unified memory. So you create a memory region. Both the CPU cores and GPU cores can access. Threads can access, and the size of it is it contains 4,097 integers, and you call that, and you synchronize, and you print the values, and then you free the memory you allocated by using CUDA free, and check CUDA error. Okay, shows how that is the code. I mean, which is really simple. And let's see what it does. Okay, so we have 33 blocks, and this many threads. Sorry, so let's also print something else, which is the number of threads that you initiate, right? So this is blocks times threads. Okay. So it looks like I initiated that many threads, but that many threads is dangerous. Why? Because I only have that many elements. So I don't have 4,200 something threads, elements. I have only that many elements. So that thing is, in fact, weird, right? So I shouldn't be able to do this operation because I am trying to access 4,098, 4,097, 4,090 something. So it goes like this because there is 32 blocks. There are 32 blocks where each of the 128 threads are doing something, should do something, must do something. But the last block, I only need to use a small number of elements, right? So from that, only one, because 4,096 is 2 to the power something, right? So that divides 128, and only one thread in the last block should work. But this is not the case here, okay? So, but the GPUs, as you see, although we have this debugging thing there, I mean, it doesn't complain anything. But if you do something like that, CUDA mem check, let's see. So it says that there is an invalid global write of size 4. Yes, we are doing the memory write here, and we are accessing the wrong location, and we are doing this access wrongfully 127 times. One of them is correct for the last block, but the rest is not. So I see many of them. So if you do, for instance, mvprof a.out, then as you see, there is something here, there is some kernel here, so it doesn't produce you again error, but CUDA memcheck tells you that. It doesn't give you the exact location though, okay? So that's, so this error is here, yeah, but it doesn't give you the file, the place in the file, in fact, okay? So if you compile it, what was it, line info? Yeah, as you see now, it gives me the statement. So line 14 of main.cu. Well, it is simple now. I know where it will be, but so this is here. Okay, so it gave me also the statement, the instruction that I perform this via memory access. Okay, how can I fix that? There is a very common pattern that you can have. So this is okay. If I is smaller than n, then do this operation. Otherwise, don't do anything. So the first 32 blocks, we'll skip that. So it will always be okay. But the last one, for the first thread, it will go inside. For the last 127 ones, it will go outside. So we'll not do anything. And let's compile it again. Let's run it with CUDA check. And as you see, it is now error free. Okay. So if we call this here, let me check something. So again, this is error. It should give me some error, right? And I don't want to call. So as you see, these are really silent things, and you need to use CUDA mem check. You need to use this kind of error checking as much as possible to understand what's happening. So for instance, let's put this here. And let's give times something like this. So I'm trying to allocate that much memory. No, there is something wrong here. Huh. Okay, so this, yeah. So this doesn't access, but now it gives me CUDA failure main.q out of memory. Okay. So yes, okay, so this makes sense. Okay, so now as you see, if you do something wrong, this CUDA check error catches it. Otherwise, you will not be able to catch it. But CUDA mem check does a better analysis in terms of memory accesses. So it is slower though. So if your application takes like 30 minutes to run, CUDA mem check will be kind of hard to execute. But still, I mean, it is giving you a very detailed analysis of memory accesses happening. Okay, any questions about this? There is a question. Can we run a detailed runtime analysis containing information like branch prediction accuracy? There is no branch prediction on GPUs, if I'm not mistaken. For CPUs, yes. For CPUs, there are perf commands, and you can get many performance metrics. For GPUs also, you can get performance metrics, but I am not sure if branch prediction is one of them, because you don't, I mean, simply. Okay. Let's do the mem check, the GTP. This will be for tomorrow. NVProf. Oh, one thing. Maybe I can also show you this. Suppose that I'm not printing anything. Suppose that I'm not freeing. Suppose that I'm not doing error checking, but I'm executing the kernel. So this is again something for the beginners. So if you do this, and if you run it with NVProf, out. Then you see, we call the kernel here, but we didn't see it here. Okay, there is no there is no kernel call. In fact, there is, but our application is exit because the application exit because again kernels are non-synchronizing, so asynchronous, and the thread continues and returns 0. So the device synchronize. Gives you a synchronization, a barrier for the thread to wait the kernel execution. And now you need to see the, that was an error in this code. So now we need to see something being called GPU activities here. The kernel is called one time, and it took 600 microseconds. Okay, so now we know how to write kernels. We know how to transfer data. You know, in fact, you know how to code GPU. You can do things, simple things on the GPU easily. Let's continue. So some of this will be a repetition, but the rest will be more examples. There will be code pieces here. We can talk about it. You can again ask questions from the Q&A session. Let me do this and let's start. So the CUDA parallelism model. So parallelism, we in fact covered some of these in the first slide set while talking about how to parallelize things, how to do computing, but we didn't talk much about the dividing the work to the tasks, okay, and map the tasks to the threads. So this kind of pattern and the step-by-step thing doesn't usually arise on the GPUs. You need to consider the grid hierarchy, and after that the work is here. So you need to know just how each thread will do what task. Okay, so that's the important thing for you. So parallel computing, the fundamentals of parallel computing, it requires that the problem can be decomposed into sub-problems that can be safely solved at the same time. Otherwise, it is inherently sequential. Even if you have 1 million processing units, it won't work. Parallelism won't give you improvement. So the programmer structures the code and data to solve these sub-problems concurrently. The goals of parallel computing is to solve problems in less time, so that is strong scaling. The same problem, you increase the number of threads, the time reduces, so it is strong scaling. To solve bigger problems, you have the same machine. Here, for instance, like 2 threads, and you have 2x job, so you have some execution time. You now have 4x job, but 4 threads, you have the same execution time. Maybe 1000 x job, 1000 threads, you have the same execution time. So this is what you want to achieve, and this is called weak scaling. And we want to achieve better solutions. The more computation that you can do, the more you can get close to the realistic setting, realistic ecosystems to observe what will happen if you really build that. So this is, we can skip that. So synchronization is, you have multiple threads working concurrently, right? And what you want to achieve some time to time is making the threads wait for each other or making threads communicate with each other. So you need synchronization for that. And barriers, this is the common term that is being used also in message passing environments, message passing parallelism, barriers. So they make threads wait until all threads catch up. So you wait, and as long as you wait, you also lose the opportunity to work, so you waste your processing power. So do not use barriers if you do not need them, but you will need them for some applications that we'll also see in this slide. And there are also things called atomic operations. So if you are summing, for instance, billions of elements, you can do this in parallel, right? So you can divide this billion elements into chunks. You can assign each thread to compute the partial sum of each chunk, and after that you can sum the results. So summing these partial results, it may mean, based on the implementation, that you add it to a common value, the output, okay? So it is shared among these threads. And if 2 threads tries to write that location at the same time, then some of the operations, the addition operations, the reduction, this is what we call as reduction, some of the reduction operations will be lost. So some of the partial values will not have an effect here. Because it doesn't work sequentially. So what it does is, these threads, two threads, try to write the same location. They first go and get the data from there. What is there? Maybe 5. So this guy has 1 at hand, this guy has 2 at hand. So I want to have 8, 5 plus 2 plus 1. But what happens is, they both read 5, they bring it to their register, they do the addition operation. So this has 6, this has 7, and they write it back, and I will see either 6 or 7, but not 8. Okay, so either one of them will be lost here. So atomic operations solve that. So you say that my operation is atomic. When you say atomic, it's indivisible. So what's indivisible? So this thing is indivisible. The go and get, do the addition, and write it back part is indivisible. So it cannot be interleaved by another operation, okay? So which means that 5 plus 1 will be executed first, then this guy will go and get 6, and after that it will say, okay, this is 8 now, and you will write 8 back. Okay, so atomic operations are available also on CUDA. So you can perform synchronizations also by using them, and they are much faster, much more, they have less overhead compared to synchronization barriers. So there are multiple parallelism models like SPMV, master worker. So all the tasks are at the master, the workers come and get one chunk, do their task, give the result back, and after that get another chunk. And so it is working like that, master worker. Loop parallelism. So you have an iteration space, like maybe for I is equal to 0 to 1 million, 1 billion. So you divide this for loop parallel loop iteration space into multiple chunks. You assign one chunk to each thread, and you continue. So fork join, there is a master thread coming, doing some sequential work, and after that you say that, okay, I will need 3 threads, so you fork. So each of these 3 threads will do something, and after that they will join again. Okay, so these are the models, these are the paradigms that you can apply. Most of them are hidden, by the way. So based on the library you use, so if you, for instance, in OpenMP, you say pragma-OMP4, then pragma-OMP parallel 4, then you have loop parallelism immediately. So you don't need to do advanced work here, but you may need to consider the scheduling of these chunk executions, okay, loop iteration space chunk executions to have a better load balancing. But this is the concept that you can also find other parallel computing course. So this is out of scope of this GP programming course. Okay. So SPM, the single program multiple data, this is the CUDA grid model. In fact, we already covered this. And SIMD, this thing is happening also inside CUDA grids for adjacent 32 threads. Okay, so the 32 threads, they are controlled by the same program controller, and that's called a warp. And you don't, as I told you, you don't want branching. They will execute the instructions at the same time by using different data. So this is why you may want to go without conditional free execution. I mean, even if it costs you to add redundant code, believe me, redundant operations, if you have a branch-free code, you are almost good. There are also other things, code optimizations, performance optimizations. Again, these will be covered tomorrow, like memory coalescing, for instance. Okay, so let's yeah, okay, so typical SPM, the program phases. We already did this, by the way. Again, this is just conceptualizing the things that we have. So you initialize, so which means that you have a localized data structure and communication channels. So obtain a unique identifier. So the global thread ID, we were always saying global thread ID. And I mean, we were interested in global thread ID because we have one-dimensional data. So the global thread ID will give me the data item, okay? The operation that I need to perform, the data items that I need to process. If I have a two-dimensional computation, and I may need two values per thread, in fact. So to find which element do I need to compute, okay? We will have matrix multiplication example again in this lecture. So obtain a unique identifier. In OpenMP, you can get the thread ID, OMP get thread num. So in CUDA, there are ways to do that. We already saw. So this distributed data part, we didn't do it, but in fact, by finding the unique identifier, you distribute the data automatically, right? And you run the core computation, then you finalize, and then you're done. So that is what we are doing. So let's go to here, okay. So this is the device code for vector addition. We already saw this. Again, by looking to here, you can understand that your blocks are one-dimensional. Your grid is also one-dimensional. From this part, you understand that your grid is one-dimensional. Sorry, your block is one-dimensional. From this part, the right operand of this addition operator, you understand that your grid is one-dimensional. Okay. So you find your global thread ID. So if I is smaller than n, this check is required, as we saw before. Ci is equal to ai plus bi, and you are done. Okay, so let's dissect this a little bit more. And you call it here like this. And you can call the ceil function instead of the syntactic sugar that we did, like how many elements do we have? N, okay. So you can have n plus 255 divided by 256, and this will give you the same value here. Okay, you can also use ceil. You can use these things, we already did. So this is an equivalent way to express the ceil function here. And this time we use three-dimensional objects to specify the grid dimensions and block dimensions. And so what happens here? So you call the kernel, the grid is created, the blocks are created. How many blocks do we have? 256. These 256 blocks are distributed to the streaming multiprocessors on the GPU. We have multiple of them on the GPU. And every thread inside each block computes the global thread ID, they do the computation. So what's the magical thing about device global? We didn't see the device, right? But we saw global. So what is the magical thing about global? So what happens when you put global in front of the kernel function definition? So global defines a kernel function. You already understood that. And these things are 2 underscore characters. Okay, so not 1, not 3, 2. So a kernel function, it doesn't return a value. It is, again, asynchronous. So you just execute it and continue. So you don't wait for the result, in fact. So this thing is executed on the device, but this is callable from the host. Okay. So until now, what we didn't call a kernel from another kernel. We only said that we have a main function and we are calling a kernel from it, right? So we are calling a device function from the host, and this is what global means. If you specify your device function or as device, so this device function is not a kernel anymore. You are not calling it from the host. It's a device function. It is special for the device. It is executed on the device. It is callable from the device. So you may guess that, why can't I do both of them? Okay, so you can have a function which is callable from the host and executed on the host, or a function which is callable on the device and executed on the device. So you can use device and host together. And host is optional if used alone. So if you don't want to say device host and only want to say host, don't do it. Main, for instance, is a function like that. And we didn't specify anything about the main. So it is callable from the host, executed on the host, but we didn't type host in front of main, right? So this is the distinction between device global and the host here. So we, in fact, so MVCC compiler, as I told you, it forwards the host code to the host compiler. It forwards to, it handles the device code, in fact, by itself. And after that, you have your heterogeneous computing platform. You have a code, you have a program, in fact, that runs time to time on the CPU, time to time on the GPU, maybe at the same time. So you can do overlapping also. Everything is possible after that point. So we covered that, but let's do this again. Because this is the most popular question when I teach CUDA programming. So as you see, we have 2-dimensional grid, 3-dimensional block, 4 blocks. Each block contains 16 threads. So 4 times 16, 64 threads in total, right? So let's try to do something with the 2-dimensional example. So we have an image. Suppose that you have an image of size 62 times 76 pixels, okay? And you decided that your blocks are 16 by 16 blocks. So how many blocks do you need? So you first need to understand that. To cover each of these pixels by assigning 1 pixel to 1 thread. That's what we want, okay? So we want 1 thread to process 1 pixel. And we have that many pixels. And we have these blocks here. And due to, so mapping, this is the most natural way of mapping the threads to the pixels, right? So you don't say that, okay, this thread performs something on this thread, the one on the right performs something here, this thread here performs something here. So you don't do something like that. You say that, okay, 16 by, I will cover that part, so some 2-dimensional part in this image with a 16 by 16 block. Okay, how many blocks do you need? In fact, the number doesn't change based on how you do it, but the computation is easier. So 62 and 16. So to cover that part, so to cover that part, in fact, right? So let me see. 62 by, yeah. So you need to have 4 times 16 at least, okay? And times 76, so that part, you need 5 blocks here, you need 4 blocks here. So in total, you will have 20 blocks here. So overall, you will have 16 by 16 times 20, 5,120, right? Threads executed on this picture. Some of them will be useful. Some of them will work, some of them will not. So what do I mean by that? So I told you that you need 4 blocks here, 4 times 16 is 64. So the last 2 threads for each block in the lowest part of this assignment will not work, okay? And this is to 76. So I put 5 blocks here so that it must be 80. So the last 4 blocks here, again, they won't work. Okay, so they will do nothing. But this is a small portion, and since they won't work, it doesn't matter too much. So we won't lose too much from the performance. It's not like we are launching 10,000 threads and only 1,000 of them are working. We are launching, what was the number? 5,120 threads, and maybe, yeah, 2 times 5, 4 times 4, maybe 50, at most 50. Yeah, at most 50 of them are not working. Okay, so we covered that part. But again, this is a repetition. These are important things, so let's do it. So row major layout in C++. Okay, so we have this 2-dimensional memory layout. And this thing, when you lay out it like this, it will correspond to this. So from here to here, so from here, you will see that this is the image in the memory, right? This is the image, sorry. this is the image in the memory. And this is how you map to the data to the global thread ID, in fact. So 00 goes to 0, 01 to 1, 02 to 2. How you do that? The same logic. So I already did this 2 times to find the location of a thread inside the block, or to find the location of a block inside a grid. So this is to find the location, the ID, in fact, of some data element inside the 2-dimensional structure. So you multiply row times the width, and you add the column, and you obtain this, okay? So this is the source code. This is the source code of a picture kernel. So let's dissect this again. There is we have the computation. We need to find the unique IDs, which will give us the data. We will perform the job, and we are done, right? So let's do it. Okay, picture kernel, calculate the row. By the way, the output input, so the operation is really simple. So we are, let's see, we are just multiplying each pixel value by 2. So that's the operation. That's the thing that we want from GPU threads. There is a picture, we want to multiply every pixel value by 2, okay? So the row number of the thread, this thread, as you now know, this code will be executed by all the threads. So each thread needs to know its row and column of its pixel, okay? So what's the row? So block IDX, why? Blocks are 2-dimensional, right? Grid is also 2-dimensional here. So block IDXY. So what's block IDXY? So this is the coordinate of the block, right? So I need to know where am I here in the image. So in this location, so block, sorry, in the height wise, okay, I need to know where am I. And then I'm multiplying it with block dim-y, okay? And I'm adding thread IDXY here. So let's try to understand this. Block IDXY, block dim-y, and thread IDXY, okay? And the column is IDXX, dim-x, and thread IDXX, okay? So this is the Y part, and this is the X part. So this picture here, you can consider the trans, but it's not important. So I am here. So I am this thread, okay? So what I need to do is I need to find how many threads along in this dimension, okay? And how many threads in this dimension? They are the same. So this is block dim something, right? And then block IDX. So I need to find that value, okay? So block ID here. So if I find that, and if I multiply it with this value, then it will increase my height this much. So I will find the value here. I will find the row ID here, okay, for this thread. Then I need to add my Y value on top of that, and it will give me my row ID. And the column the column computation is the same. So this is the in fact, this is X, so this is Y. So you use it like that usually on GPUs. So what we did is but the same. So we find this value, this length, or this length, they are all the same, which is 16. We multiply it by our block ID on inside the grid, and after that we add our value here, and we are done. And to compute the other coordinate, again, I find this value, I get this value, which is again 16. For instance, let's say I am computing this, and this is 3 here. The block X value is 3, 0, 1, 2, 3. So this is 3 something, okay, 3, 2, block 3, 2. So 3 times 16, 48, and I need to add also my X value on top of that, and I find the find the column ID in the image, okay? So this row and column are computed like that, and the rest is easy. You just need to add that part, and the reason is the same that we had this. The reason is the same with the error that we found with our CUDA map check execution. So we just need to know that if we are in the boundary or outside the boundary. So if we are inside the image or outside the image, because our grid doesn't fully overlap with the image. So it a little bit extends, it goes out of bounds of the image, right? Based on this picture. So I need to exclude that threads from the computation. I don't want them to do anything. But the rest, they will work and they will do things, okay? Let's continue. So how do we launch that? Well, the pictures, their sizes can change. But the block sizes, I want to use 16 by 16 blocks. So this is constant, this is fixed. For this one though, I need to do again, the syntactic sugar. So n minus 1 divided by 16 plus 1, or n plus 15 divided by 16. This is the picture is n by n. Okay, so if the picture is n by n, and this thing is here, is the n from here, and this is the m from here, and this is the number of blocks that I have. This times this. Okay. So not all threads in a block will follow the same control flow path. We already covered that, by the way. So again, so this is 4, this is 5. So for these guys, everyone here will work, in fact, but except this region, the threads inside this region and the threads inside this region. Okay. So these will be the blocks. The dark blocks here are the blocks whose threads will be fully working. A little bit lighter, so these things and these things, their threads will not work due to the out of boundary condition for exactly one dimension, either here or here. For this block, the last block, most of the threads will be working, but more number of threads will not be working compared to the previous ones, because you go out of bounds from 2 dimensions. Okay. Let's continue. So now a real world use case with the multidimensional data and the multidimensional grid and block allocation or organization. So RGB color image representation, you all know that each pixel in an image is an RGB value. The format of an image's row is RGB, RGB, RGB. So we have RGB, RGB, RGB. So we have a pixel for these three values. We have a pixel for these 3 values, and each of them is a character. They can be represented with a character. So the RGB ranges are not distributed uniformly, many different color spaces. Here we show the constants to convert the Adobe RGB color space. The vertical axis and horizontal axis show the fraction of the pixel intensity, and the triangle contains all the representable colors in this color space. But there are also other things that you can do with the images, right? Like converting these things, instead of visualizing it with colors, you can convert this to the RGB, black and white, grayscale format. So there is a formula for that. You again get the image, get the pixel. If you're a thread, get your pixel, do some computation, and write it to the output. So a grayscale digital image is an image in which the value of each pixel carries only the intensity information. Okay, and that's the formula. For each pixel, for each RGB at ij2, gray pixel ij is equal to 0.21 times R, 0.71 times G, 0.07 times B. Sorry, a little bit. Okay, so there was a significant noise coming from outside. So this is just a dot product, right? So RGB times that vector with the constants being specific to input RGB space. Okay, so let's do this thing now. So We have 3 channels corresponding to RGB. The input image is encoded as unsigned characters, which with values from 0 to 255. So this is the gray image output. This is the input RGB image, and this is the width and height of the image. So let's see. We have X and Y here. We have thread IDX times block IDX times, thread IDX plus block IDX times block DMX. The same thing that we did before to map the threads to the pixels. So let's again try to understand what we are doing. I want to find the coordinate of this guy. I will find the height of each block. I will multiply it with this coordinate, my coordinate along this dimension, okay, of my block. And then I will find the coordinate for these threads in my block. And then I add my value on top of it, okay? So for the other dimension, I find this length, this length, this length. I multiply it with 3 because there are 3 blocks before me, and this is the third block. And this is in the grid in this dimension. So I add my value and I find my row and column based on that. Okay, if X is smaller than width, Y is height. If I'm out of bounds, I do nothing. If I'm not out of bounds, I do something. So I get gray offset. So gray offset is equal to Y times width plus X. So why do I have that? So here, these images, as you see, they are one-dimensional. So, okay, I have the data in two-dimensional format in my mind. I find my X and Y coordinate values on the image. But where is this data? Where is this pixel inside the memory? That is something else, okay? So because this is one-dimensional representation. So for the gray offset, which is the output, which will be used for the output effect, there is 1 character per pixel because it's a grayscale image. And then I can compute it by Y times width plus X. Again, the same logic. We are not doing something fancy here. For the input image, I need to multiply it by 3 to find the location, the R value, the red value of my pixel, because it is RGB, 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 RGB. So for the third one, for instance, for the third pixel, I need to skip 3 times 3 values. So I'm skipping these things here, okay? And then this is the R value, this is the G value, the next one, this is the B value, and I get these values. And then I do this dot product and write it to the output image. So that's the operation, in fact. So this is done. So let's do blurring. So how do we do blurring? But let's give, in fact, a break here. So it is 3:05. So let's start at 3:15. So let's give a 10-minute break here. In the meantime, if you have questions, if you want me to cover the things, some of the things again, I can do it when we are back, okay? There is a question in the chat window. So isn't the color defined by RGBA? Yeah, RGB. What's A? I don't know. So this is red, green, blue. Yeah, okay. If you have something to ask, again, ask it through the Q&A part. Okay, so we have 10-minute break. So let's start. In this application, for every pixel, you do not only need the data from your pixel, but you also need data from your surrounding pixels. So we have this image and we want to transform it to be like this. So for every pixel, I will go and I will have a window. I will go and get the values inside this window. And after that, I will do something with it. Okay. So that's the blurring box. So for this pixel, for instance, I will go and process. I will need the data, okay, for these pixels, and after that, I will sum them up. I will do something with them, and I will write the result back here. Okay. So again, the mapping is easy. So we already learned how to do that. We find the column and the row for our pixel. So each trace does that. And after that, if the column is smaller than W, if the row is smaller than H, then we are inside the boundary, then we will do something. So let's see, what do we do? So here, this is the computation. This is how you compute the result, the values that you need. So you have pixel value, you have number of pixels. A pixel value will be the sum. So as you see, there is the input image and the output image. So for every pixel that is so our window, so let me start by describing the window. So the window size is 2 times blur size. So if I am this pixel, I will go 2 times, I will go blur size here or blur size here. So this is the width of my box, and blur size here, blur size here. So this is how I define my window. And this is why I start from minus blur size, and then I go to blur size +1. And so this is blur row. So we have blur color, blur, again, it's going from blur column, sorry. So minus blur size to blur size +1. And as you may guess now, we add the blur row to here and blur col to column. And after that, we find the pixel that we want, okay? So at the beginning, so you are here, this is your pixel, you start from here. Then you, let me see, yeah, columns change, right? So you go over these pixels, and after that, these pixels, and after these pixels, and it goes like that. So you visit every pixel there. But again, you need to check if your pixel inside the window is inside the boundary. So you do this again. These checks are here. This time you have additional checks because you can go to negative, unlike this one. So you increase the value in the input image. Sorry, you add the value to your pixel variable in the input image. And after that, you increase the number of pixels that you process by 1. And then you write pixel divided by number of pixels to the output image. So again, this is the mapping from 2-dimensional to 1-dimensional organization. And this is again the same 2-dimensional to 1-dimensional organization. This is for the visited pixel. This is for you. Okay. There is a question. Okay, that's not a question. And chat, yes. Grayscale images are represented by a single intensity value per pixel, where each pixel is only 1 byte. Yes, okay, good explanation, thanks. So, the next objective is learning how a CUDA kernel utilizes hardware execution resources. So this is how it happens. we have our thread grid. In this one, it is again two-dimensional. The blocks assume that they are one-dimensional. It doesn't matter, in fact. So what we have is these things are distributed to the streaming multiprocessors inside the device. So these are actual architectures. So this is an architecture. So this is physically streaming multiprocessor. This is the GPU. So this GPU contains two, for instance, streaming multiprocessors. This GPU contains 4 streaming multiprocessors. So they are distributed in a round robin fashion. So 0, 1, 2, 3, 4, 5, 6, 7 for this GPU with 2 multiprocessors. 0, 1, 2, 3, 4, 5, 6, 7 for this GPU with 4 streaming multiprocessors. So each block can execute in any order relative to others. There is no guarantee on the order of execution for any block. Hardware is free to assign blocks to any processor at any time, and a kernel scales to any number of parallel processors. Okay. So threads are assigned to streaming multiprocessors in block granularity. So the block is assigned to a streaming multiprocessor. In this architecture, in this GPU architecture that's being talked here, up to 32 blocks to each SM as resource allows can be assigned. So for the Volta architecture, Volta streaming multiprocessors, for instance, they say they can take up to 2048 threads. It could be either, for instance, 256 threads per block times 8 block, or 512 threads per block times 4 block. So based on your number of threads inside the block, the number of blocks that you can assign to your GPU, a single streaming multiprocessor, changes. And this also will change the occupancy for some GPUs especially. So streaming multiprocessor maintains these thread IDX, block IDX values, and they manage the thread execution. They schedule the thread execution. So here with the SIMD units, this picture that we saw before becomes this. There is a single control unit, but multiple processing units. We already covered this, by the way, so there's nothing fancy. This is what single instruction, multiple data tells us. And then this is important. Each block is executed as 32 thread warps. This is an implementation decision, not part of the CUDA programming model. Warps are scheduling units in streaming multiprocessor. So a block is being executed on a streaming multiprocessor. Suppose that it has 256 threads. So it means that it has 8 warps. A warp is the unit of execution, scheduling execution, or execution scheduling. Yeah. For the streaming multiprocessor, so warp comes, warp goes away, warp comes, warp goes away. It's not like thread by thread. So warp comes, these 32 cores executing the threads of this warp are being controlled by a single controller. They do the same thing with different data, and they go out whenever they request a data from the memory. Whenever they are said that, okay, I will wait for this, they will pay the latency. So warp goes, and then another warp comes, and it again works, starts doing something meaningful. Whenever this warp does some memory access. By the way, don't forget, there is a single controller. So when a thread does memory access, the others also does some memory access, right? And they wait, so this goes out to the queue, and after that another one comes, etc., etc. It sounds expensive, right? So I mean, you are making 32 threads leave the GPU, one streaming multiprocessor, and then another one comes, right? So this is done very efficiently on the GPU because the resources, all the resources that warp uses, the registers, the register values are kept there. Okay, so it's not like we are removing it, putting to somewhere else, And then another warp comes, put its resources, put its data state on top of the previous warp state. So it doesn't happen like that. The state stays there. Okay, so the state stays there. So when a warp comes back, it continues. So there is zero overhead for while doing this scheduling. So featured GPUs may have different number of threads in each warp. Currently, it is 32. So example, if 3 blocks are assigned to an SM and each block has 256 threads, how many warps are there in an SM? Okay, so 1 block has 8 warps, 3 blocks has 24 warps then. Okay, so 24 warps are being executed if you assign 3 blocks to a single SM. So this is the thing that I just told, zero overhead warp scheduling. So warps whose next instruction has its operands ready for consumption are eligible for execution. Eligible warps are selected for execution based on a prioritized scheduling policy, and all threads in a warp execute the same instruction when selected. So then why block size is important, why number of threads inside the block or block organization is important. So let's consider this. For matrix multiplication, using multiple blocks, should each block have 4x4, 8x8, or 30x30 threads for volta? So you need to know something before, right, to answer a question like that. You need to know how many threads each SM in a volta architecture can execute at the same time, right, at most. So if we have 4x4 blocks, we have 16 threads per block. So that value the value that I just told, the maximum number of threads per SM is 2048 for volta. So which translates to 128 blocks. However, each SM can only take up to 32 blocks. So there is this limit also for volta. So only 512 threads will go into each SM. Okay, so it's not like you are utilizing this streaming multiprocessor to the most. Okay, so it doesn't, I mean, you could put more threads, still you didn't, you are not capped by that. But since you use a very small block, then you are limited by this number, this 32 here. For 8x8, we have 64 threads per block, which, let me see, yeah, with 32 threads, then with 32 blocks, it makes 2048 threads, so it uses full capacity, unless other resource considerations like shared memory usage, register usage overrules these numbers. For 30x30, we would have 900 threads per block. Only 2 blocks could fit into SMY because the first block 900, the second block 1800, the third block will not fit. So you still do not utilize this limit here, and you lose like 10% of the number of threads that you can put there. So this is the best, it looks like this is the best one in terms of utilization. Okay, so there is a question. By the way, let's go back to here. Maybe I can. Samples. Okay, if you install CUDA, there is samples, CUDA samples are coming. So if you execute that, the device query one, if you compile everything there and execute the device query one, which is under the utilities here, okay. You see that I have 4 GPUs on this machine. They are, in fact, not that recent ones, so they are old. I have a Titan X. I have GeForce GTX 980, another GeForce GTX 980, and somewhere here another Titan X. Okay, so let's see the total amount of memory: 12 GB for Titan X, 4 GB for GTX. This guy has 3,500 cores. So if you from this you can in fact have memory clock rate and memory bus width. You can have the amount of data you can feed gigabyte per second for this device. We have some L2 cache of 3 megabyte, and we didn't talk about shared memory, but this is important. These two values are important. Total number of registers available per block, that is important because, yeah, so this one, for instance, 2048, right? So that's the maximum number of threads that you can fit inside an SM. But if you thought this total number of registers available per block, it can be also a limiting factor without you reaching to this guy, okay? And again, a simple error that the beginners make. I made it like many years ago and tried to find the error for like 2-3 hours. So this maximum dimension of a thread block. So although you can fit 1024 blocks, sorry, threads per block, okay, so you can go on up to that much, not more than that. The maximum dimension size of a thread block is this, and the maximum dimension size of a grid size is this, okay? So if you exceed this value, I mean, at the beginning, this value was not that large, in fact, but what we were doing is we were assigning a vertex, a thread to a vertex of a graph, and we have like billions of things, so we needed to go to two-dimensional grid size because of this limitation. So that was the problem. And yeah, you can get these numbers that we were talking about by using device query, or from CUDA API. You can query everything here, in fact, programmatically, and after that print the result, or a selected subset of this. Okay. So we are done with this. But let me check. This. Okay. So let's do this. This is, we know enough things about this. Better. I won't change anything, in fact. So let's see. Again, managed memory is used, unified memory. We have three, it looks like we have three vectors, and we are doing again vector addition. So A plus B is equal to C. This is what we want to compute. This is the common thing. Okay, CUDA free, CUDA device synchronized, CUDA check error, everything is here. But it looks like we can do the addition in two ways. So we have two-dimensional grid, two-dimensional block, and 32 by 32. Let me see. Yes, 32 by 32 threads, so 1024 threads in a block, which is possible because I can support that much, and that many blocks overall. Okay. But I can do the addition in two ways, as I told you. So what's the difference? They look the same. The difference is this. This is I is computed as block IDX block dim X thread IDX J IDX Y dot Y dot Y. Here I is computed with dot Y dot Y dot Y. J is computed with dot X dot X dot X. So what's the difference? In one of them, with 32 by, consider a 32 by 32 block. So these 32 adjacent threads, in one of them, they compute the additions, vector additions for adjacent locations. In the other one, This guy computes this thread in a block. This thread computes that computation, performs that computation. This thread computes the next 32, the 32 next computation, okay? This thread computes the computation, which is 32 times 32 on the right again. So, I mean, they are like jumping, okay? So in terms of the computation, in terms of the iteration space, they are jumping. Okay, good. So which one is which? So you can understand that from IDX, I think. So column is here and column is here. So plus column is the one that is used to decide the next adjacency, right? So because it's plus col. So column is here. And we are giving J here. J uses thread IDXY. We are giving J again here. And this is the one that does the adjacent operations. This is the one that performs the jumping based thing. So let's try to understand what's happening here. NVCC. And well, I mean, they work obviously, but let's see what MVProf tells us. So MVProf tells us that that thing at V1 took 10 milliseconds, whereas at V2 took 140 microseconds. But I told you that this is the adjacent one, right? So that it shouldn't be like this. So what's happening here? Don't forget, we use managed memory. At the beginning, it is on the host. When I call V1, these page faults happens. And this data is transferred to the GPU. So this thing is in fact, or if you call it only once, this thing is in fact computation time plus data fault, page fault, and data transfer time. So it's overlapped, right? So it contains both of these things. So this one. So at V2, it looks like it is 90 times faster. Okay, this is adjacent, but 90 times faster? Come on, it shouldn't be the case, right? And the data transfer time is the reason. So let me do this maybe. Same for this one. Let's see what happens if you do this. And in fact, let's use -03. Use -03. It doesn't hurt to use it. And it gives you performance boost. Okay. So as you see, the maximum time is 8 milliseconds for now V1, because that's the first one. The minimum time is 500 microseconds. And the average is 900. Yeah, so the average is here. But the minimum one is the important one here. Okay, so because this is the thing that represents the execution without any data transfer. And the other, it didn't change. As you see, it is the same as before. So it looks like doing this adjacent data accesses within a verb pays off. It makes you 3 times faster, 4 times maybe faster. And you will understand why tomorrow, because tomorrow there will be the performance course and the debugging and profiling course. So you will do these kind of things. But you need to be careful about branching. You need to be careful about coalescing, in short. Okay. Any questions about this? And there's a question. If we have multiple kernels, should we explicitly express data dependency, or can CUDA detect it? The CUDA doesn't detect any data dependency. In fact, you need to say that this will work before this. This should work after this. If you have multiple kernels, and probably you are asking the question because kernels are not synchronized. When I say asynchronous, it is like the kernel is submitted, and the other if there is another kernel call just after it, the thread will go and execute the kernel. If there is another kernel after that, the thread goes and execute the kernel. So it's kind of a mess, right? If these kernels are dependent to each other. So if the first one must work first, the second is the second, the third is the third. But we will see that if time permits, they are going to stream a queue, in fact, and they are executed one after another. So although CUDA doesn't depend anything, doesn't detect anything, any dependency, by submitting them to the same queue, you are saying that this must run first, this is the second one, this is the third one, and we call these queues as streams, okay? There is another question. Is it called memory coalescing when we use add v2? Yes, so memory coalescing, let me describe it with one sentence. If you have a verb, and if the memory accesses, don't forget, they are being controlled by the same controller, so their memory accesses will be at the same time. If their accesses are within the same memory block, okay? They don't need to be sequential, like, so the access doesn't need to be like this or like this. So they can be like this. So this is here, this is here, this is here, but close locations, okay? And we say that memory accesses are coalesced. Okay. Let me check this. Matrix multiplication, but for that we need to cover something else. Okay. So probably this will be the last slide set. But I will also add the actual last slide set, the streams and the example about them. So you will be able to work on that. And if you have questions, you send me an email. Okay, I will answer. Okay. So the blur kernel, we have a pixel, we assign a thread, that thread searches within the pixels within a window, adds the values, counts them, takes the average of the value and write it back to the output. So that's the blur kernel in short, right? But this thing here, this statement, this is going to global memory of the device. So in here is the input image. It is stored on the global memory of the device. Okay. And so if I'm a pixel here, I am a thread processing this pixel, sorry. There is the next thread processing the next pixel, and their windows overlap significantly. So they probably require the same data, except the boundaries, right? And the next pixel, the next thread is the same, the next thread is the same, although the overlap decreases compared to the window, when compared to the window of the first thread and pixel pair. Still, I mean, there is a huge amount of overlap, especially blur size is like 16, especially it is more than that. I mean, 512, 1024, it doesn't become like that. Maybe 4x4 windows, 8x8 windows are used, but still. So why do I need to go to global memory multiple times for the same data item? There's the question you need to ask yourself, because global memory accesses, they create latency significantly. Although we are hiding it, it is still there. And memory accesses, global memory accesses are expensive compared to shared memory accesses that we will learn today again in the slide set. So all threads access global memory for their input matrix elements. One memory access, 4 bytes per floating point addition. So this is, let me see. Yeah, this is matrix multiplication. So this, for this one, again, I mean, let's restate the verdict. We can do optimization if we have a location that is accessible by these adjacent threads or the threads inside the block, for instance, which is if that memory is faster than the global memory, then I can do much faster blurring here. So let's talk about matrix multiplication, okay? All threads access global memory for their input matrix elements. So one memory access 4 bytes for floating point operation. Why one memory access per floating point operation? For per floating point addition, it says. Let me see. Yeah. So this is again for blurring that, because one memory access per floating point addition. So 4 bytes per second of memory bandwidth flops. Assume a GPU where peak floating point rate is this 1,600 gigaflops with 600 gigabyte per second DRAM bandwidth. So this much bandwidth is required to achieve that theoretical rate, okay? That gigaflops. But we are limited with this one, and this only gives us that much gigaflops, which is much like 10% of the gigaflop that we have. So this limits the execution rate to around 10% of the peak floating point execution rate of the device. Need to drastically cut down memory accesses to get close to the 1,600 gigaflops. So the first thing that you need to realize is this thing. Once you start with this, everything is in fact clear. So let's do it again. One memory access per one global memory access per operation is done by blurring. Why? Because of this, okay? We bring the data, we do one operation, okay? So how fast you can bring the data? You can bring that data, right? 600 gigabyte per second. So 4 bytes per floating operation. If you divide this to 4, then it will give you this number immediately. So you can perform that much gigaflops only. But your peak floating point rate, this is coming from the GPU. You don't need to find it. You don't need to compute it. Is 1,600, so it is 10%. So you can do better if you use shared memory. So that's the verdict. For matrix multiplication, we have this guy here. We have this guy here. We want to multiply them, and we want to compute P. So M times N is equal to P. Okay, so this is the operation. So the simplest kernel that you can write is here. Global void matrix multiplication kernel. This is matrix in a one-dimensional format. This is matrix N in the one-dimensional format, output matrix in one-dimensional format, one-dimensional organization. Maybe it's better to say it like that. And these are square matrices, so N by N matrices, and this is width is equal to N, let's say, okay? Oh, sorry, N is already used, so let's say width. So again, the row index, we did it before, IDXY, IDX, dim-dim-Y, IDXY, and we compute the row for a thread. So this is the output location. So this thread will compute P, row, and column. So the matrix entry P, row, column. Okay, so this thread will compute that. And to do it, it needs to go and get the row from M, column from N, and perform a dot product operation. Okay. So let's do it. If row is smaller than width, column is smaller than width, we are checking if we are inside the boundary of the matrix, because width may not be divisible by our block dimensions. So this is the partial, this is the value that we are using to sum up all the dot product partial values for in K from 0 to width. So this is a dot product operation where the vector is M row and column, okay? So M row times width plus K will give me the entries in the row of M, and K times width plus col will give me again the entries in the column col of N. And just one simple observation. So this is the loop, right? And column increases with thread ID XX. So the next thread I have will have the one different column. The next thread I have will have the next column. So if I have column 1, the next thread in the same verb will have column 2. The next thread in the same verb will have column 3. And the rows, again, so they will increase by this, right? So row value will increase a little bit more. Let's see. No, thread ID XY will be the same. My bad, sorry, my bad. These values are already the same, so their row values will be the same. So let's check. Row is the same, width is the same, and K will be the same. So this thing will be the same. And this thing will be called as XS. So we shouldn't have a problem here, in fact. Okay. Memory accesses, they look good. And I add the product to here. And after that, I write the value to P value. That's done. That's simple matrix multiplication example. Okay. So this is how it happens, right? So suppose that block width is 2. I have a 4x4 matrix. I have 3 4x4 matrices. In fact, block width is 2, so I need 4 blocks. So this is the first thread. This is the second thread, and it goes like that. So the first thread reads all these values and all these values. The second thread again reads all these values and all these values. So although their N values are different, their M values are the same because their row is the same, right? This is what we decided. So why do I need to go and get this element again from the memory? Every time, by the way. So let's do something different. So that's the, again, use that will come to the using shared memory part. And in the von Neumann model, you already know it now. There is the control unit, processing unit, and memory. And this is the von Neumann bottleneck, right? So now let's add something more to this model. I have a thread. Yes, I have access to global memory. It is slow. And I have registers. They are local to me. Okay, I cannot share it with another thread. But what if I have something that can be shared within the block? That means within the verb also. Okay, so that's one thing that we can do. So within the block is important. The keyword within the block is important. Why? Because we learned that, we didn't see how to do that, but we learned that there are synchronization primitives inside the block. So for each thread, for the threads inside the same block, we can have synchronization primitives. Okay, so let's talk about the terminology a little bit. So once you say, when you say something like integer local variable inside the device code, then the memory, it will be the register. So this thing will be stored in the memory. The scope will be thread. So the thread will be able to access it, and it will live as the thread lives. When you say shared, okay, You don't need to say device always, just say shared. This is a shared memory. The scope is block, so every thread inside the same block accesses the same shared variable, and the lifetime is block. When you say device integer global variable, then the memory will be global, scope will be grid, lifetime will be application. And if you say device constant, again, it's grid application, but it will go to constant memory. But again, I mean, this is constant, okay? So we will not see this, the use of this today. And it is small, and its use cases are less compared to shared memory. Okay, so the Blur kernel, you can create something like that. You can create a shared region, shared memory of size tile width times tile width, and bring the input data first to the shared memory, and then perform the computation by reading the data from shared memory instead of reading them every time from global memory. So that's the solution for your problem, for your 10% performance problem, right? So where to declare variables? We already solved that table, in fact. So global constant, you can define them outside of any function. And register and shared, this should be inside the kernel. So shared memory in CUDA is a special type of memory whose contents are explicitly defined and used in the kernel source code. Well, this is shared streaming multiprocessor specific, okay? So it's not like shared memory covers multiple streaming multiprocessors. So one in each streaming multiprocessor. There is a size, and there is also a limit for each block to use from that shared memory region. So it is accessed at much higher speed compared to global memory. Scope of access and sharing are thread blocks, where the lifetime is thread block. Contents will disappear after the corresponding thread terminates execution. Access by memory load store instructions. This is again what you do for global memory, right? A form of scratchpad memory in computer architecture. And it looks like this. So there is this multiple threads, or you can, multiple threads controlled by the same controller, or maybe you can have multiple controllers here for a block, and then they are accessing the shared memory instead of going to global memory. So this is faster, right? So tiling is important for especially two-dimensional, three-dimensional data, okay? Even for one-dimensionals like stencil computation, one-dimensional stencil computations, you can have tiling by bringing some data to shared memory first and accessing it again through shared memory. So what does it mean? So the global memory access pattern of the basic matrix multiplication kernel. So the first thread reads these elements, the second thread reads the same elements from the same matrix. And then they do some computation, right, for each memory read. Instead of that, you can bring some of them to a scratchpad space, and after that, make these read here. So you can divide the global memory content into tiles, focus the computation of threads on one or a small number of tiles at each point of time, and continue, okay? So let's skip that. We will need time. So shared memory is not the solution for every problem, every global memory access performance problem, but it works if the threads adjacent to each other, consecutive within the same block, let's say. If you can organize your threads like that, if you can map the threads to the computation like that, in a way, the threads accesses the same amount, same data items at the same time, or at close times, okay? Not at the same time, but at close times, at close time intervals. So if this is the case, shared memory is really useful for the performance. So here, for instance, threads thread 1 and thread 2, they access the same elements, right? Here and here. But this is the good one because they access the same elements within closed intervals. But here, for instance, thread 1 access this element here, thread 2 access the same element here. So that's not good for shared memory, in fact. Okay. So let's see some code, and it will be more enlightening, I believe. So tiling means this. So in the naive way, each thread accesses a row of M and a column of N. Okay. In the naive way, each thread block accesses. So each thread block here, for instance, accesses again in the naive way a strip of M and a strip of N. Okay, so this part and this part. So this is what the block will read. Okay. So let's break up this execution of each thread into phases such that the data accesses by the thread block in each phase are focused on one tile of M and one tile of N. So what does it mean? So, okay, so we have this region and this region to be accessed by this thread block, okay? What if I do this? So I have a tile here. I can have a tile here. I can do some partial multiplication, partial dot product, and store the value here. But if I do this, if I do it like this, all the threads inside the block can do the same thing, right? So that's the beauty of it. So I will have this guy and this guy, and that these threads all will work on the same amount of data, same data, in fact, at the same time. Then I will go to the next phase. So the tile is of block size elements in each dimension. And let's see, maybe it's better if I skip these. Or maybe it's better if I show you this. Okay. So this is the matrix multiply CPU code. Again, 3 loop code. So for each row, for each column, this is CPU. Okay, so don't forget. For each row, for each column, I have a loop, I have a dot product. So for each output element, in fact, I have a dot product. And that is how I access the array elements. So matrix elements A, B, and C is the output. So row times width plus K, B, K times width plus column. So K increases every time, and I multiply it with width. So for this one, the accesses to A have good spatial locality, but accesses to B do not. Because in the memory, the element K times width plus column and K plus 1 times width times plus column, they are not adjacent in memory. So this suffers from that. I can solve that by first transposing B, okay? And then after that, do the same computation. Well, there is some loop unrolling here, but you don't need to be, I mean, let's ignore that. Compilers are doing that, by the way, most of the time. So you can get the transpose of B and have also good spatial locality here. So that's the most important thing. And this is the simple code, simple matrix multiplication code that we saw. So again, column and row, these are the coordinates of each thread. So this is the location of the output a thread will write its value. And that product is here, the same code. So let's run it. And let's see the performance difference between the and the GPU. Okay, So it looks like I am using something from the OMP, and this is missing the library. So don't forget that we have -x compiler. I am passing -fopenmp to the host compiler, and it is done. Just to be sure, I mean, compile it like that. And let's run it, and let's see what will happen. So here the matrix size is, let me see. Yeah, so 2048 times 2048, okay? So we are performing around 8 billion multiplications here. Yeah, yes. And for the CPU, single thread CPU, non-optimized CPU, it took 20 seconds. The optimized, the transposed one, it took 8.7 seconds. If you do it in parallel with some number of threads, this machine has 16. It took 400 seconds. But, so okay, 16 cores, but 32 threads. So there is also hyper-threading. So this, but still the speed up is good. But even the naive GPU code performs it in 43 milliseconds, okay? But what don't we do? Let me, let's see how do we, okay, how do we measure time? So there is CUDA mem set here, and these things are here, but as you see, the CUDA mallocs, CUDA mem copies, they are not taken into account. So it's a little bit cheating, don't do it. The processing time, it is really good, but if you add the data transfer times, the results may differ. It may not be at least that impressive, okay? Let's execute it like that. In the meantime, we can go back to the code and see how we use shared memory. So tiling, right? So we have some strip from M, strip from N, and we have this. A tile for the matrix A, the input, one of the input matrices, another tile for another input, the other input matrix. Row and column computation, they are the same, but the execution is now divided into phases. So P is the phase number, okay? And the matrix size is 2048. I will perform 32 by 32 blocks. So I need to do 2048 divided by 32. So 64 phases, okay? So this will go until 64. For each phase, I first go and bring the tile, the first tile from the first matrix to the shared memory, the second tile from the second matrix to the shared memory, and then I do it in parallel, by the way, as you see, because my thread block is also tile size. So I have as many number of threads the number of threads in my block is equal to the number of elements a tile has, right? So every thread brings one element from each matrix and they are done. This is important, sync threads. As I told you, there is block-wise synchronization mechanism, simple, and this is it, okay? So all the threads in the block wait, because when the data is not ready, they cannot start to do their computation, and they will need the data, okay? So what they do is, they go and get partial dot products, and they store it to their result here. Okay. By the way, I mean, we are not changing the thread to output data mapping here. So they will still compute, each thread still computes the same output element, but instead of doing it at once, they do it tile by tile, because the threads within a block uses common elements, and they are now inside the tiles. So here, as you see, this is a shared memory access and shared memory access, okay? So all these accesses are done to the shared memory. So instead of performing one global memory access per floating point multiplication, I first bring each element to the shared memory, and after that, the rest of the accesses will go to the shared memory. Okay, and again, perform sync threads because you don't want this to be overwritten by the threads if other threads are working still on the tile. So these barriers are important, and wrapping the computation is important here. And you write the result back. Any question about tiling? Okay. So if you do tiling, then you make your GPU optimized code as 12 milliseconds. By the way, I will go over this once when I will be going over the slides, but I just want you to understand what is that in terms of code, okay? So 43 milliseconds, now it is 12 milliseconds. So this is 4 times improvement almost. But there are these. So here we have host to device copies, 3 of them. Device to host copies, 2 of them. One for the normal code and one for the optimized code. But as you see, this thing, I mean, this also doesn't take too much time, okay? Yeah. So CUDA malloc, it takes a little bit more time. So 100 something. So, okay, 124 milliseconds. But the first access is the most expensive one probably. So you can consider this guy maybe. And there is some data transfer cost. So maybe 3-5 milliseconds. So you need to add like 10 milliseconds on top of this. The data is small, by the way. If you have an n-cube complexity algorithm, that's good. So GPU transfer times is not important, right? The complexity is important. If you have ON problem, then yeah, data transfer times should matter more and more. So in short, then for dense computations, for regular computations, for linear algebra operations, deep learning, for instance, GPUs are superior to CPUs. And tiling is a way to make the training process 3 to 4 times faster. Machine learning training process, for instance, 3 to 4 times faster. Okay, so let's go back here and let's go over it again. Okay, so let's again do this thing. These are 4 blocks, 4x4 matrices, 2x2 blocks. And this block here first reads a tile from global memory and bring it to shared memory. And then it does the same for M. And then these dot products are partial dot products. So instead of computing, for instance, this guy, this row times this column, this guy here computes only this times this, okay? And the next phase, it will do the same, okay? With different tiles, and then it will find the final result. So barrier synchronization, sync threads, this is necessary because you have a shared memory. All of the threads are first preparing the data by reading the data from global memory on the shared memory. Then you need to synchronize, then you need to perform the computation. Then you need to do another synchronization. The first synchronization necessary because you don't want some of the threads start their computation before their data is ready. The second synchronization is necessary because you don't want the data to be overwritten before you finish your computation, okay? Because maybe another thread is faster than you. He says, okay, I am done. I will go and get the next tile. So you shouldn't allow it to do. Okay. So this is the code that I showed you, in fact. Again, so this is the indexing from finding the coordinates, the same logic. You will memorize this after some amount of time, after spending some time with matrices, believe me. And to the indexing for tile 0, so I am accessing row. So for instance, I am this guy. Which data will I bring from M? From M, my row will be the same. So I will read this data and bring it to the shared memory, right? This and TX, okay? So this is my row already, right? And this is my TX, this guy, okay? So I will go and read it. At the first iteration, by the way, the phase 0. In this one and this one, I will go and get TY. So this is my TY, right? And my column. So I share the column. So this is what I do. In the first iteration, in the second iteration, phase 1. Now, let's see, my row is still the same for M. So I will bring this guy now. Then for the, so my row is the same. So what's the column? What's the value here? So I need to go 1 times tile width plus TX, okay? So this guy, and then this guy, I need to go by TX, okay? So this one. And row is the same. So this is the same for here, 1 tile times width. No, this is not correct. Tile width, sorry, plus TY and column, okay? So for this one again, and this one, so I share the column again, but then I need to go and get this one, okay? Yes. Any questions about this? And it goes like this. I can multiply tile with phase ID and it will give me the correct values. This is the same code. Okay, so what is the optimum tile size then? So each thread block should have many threads. Tile width of 16 gives 256 threads. Tile width of 32 gives 1024 threads. For 16 by 62, for 16 by 16, in each phase, each block performs 512 float loads from global memory. Why? Because tile size is 256. I have matrix M, matrix N, so I bring 1 element per thread from each of them. So it is 2 times this. And perform 256 times 2 times 16 multiplications and additions. This is dot product. For each element, I perform 1 multiplication, 1 addition. And I have 16 elements, so 1 multiplication, 1 addition, this is 2. I have that many threads and I have that many floating point operations. So 16 floating point operations for each memory load. And that's not bad. But if you increase your tile size, then that will be better. Obviously, you will reach 32 floating point operation for each memory load. The best thing that you can do is bring all the matrices to the shared memory and perform the computation in just one phase. So why can't you do that? Because your shared memory is small. Let's go back here. And shared memory size, where is it? Okay, so the total amount of shared memory per multiprocessor is 90 something kilobyte, 96 kilobyte. If you have 2000 by 2000 matrices, that is what, million? Yeah, million elements, right? So 4 megabyte per matrix. So if you want to bring both matrices, it's 8 megabytes. You don't have that. You have only 96 kilobytes. And furthermore, 1 block is 48 kilobyte. Well, one block can use only 48 kilobyte of shared memory. If you want to use, if you use further more, then you will get some initialization configuration, something like that, some error stating that your initialization parameters are not good. So tile size is important. And another thing that limits you is with this computation pattern is, so you have tile size, tile width times tile width threads, okay? And you already know that each streaming multiprocessor which you assign a block to cannot have more than 2048 threads. So that's another thing that limits you. And I think these are the things, yeah. For a streaming multiprocessor with 16 kilobyte of shared memory, by the way, shared memory size is implementation dependent. For tile width is equal to 16, each thread block uses 2 kilobyte of shared memory. Then it means that you can have 8 thread blocks. 8 thread blocks times 256 threads is what? 2048. So that's good. You can run everything at once. I mean, that's not a problem. But this allows up to that many pending loads. As I told you, all the not all, but most of the magic behind the GPUs having latency hidden, right? So these are the pending loads at the same time. So that's not good. That's not bad. Sorry. So the next tile with 32 will have 8 kilobyte shared memory per usage, per 8 kilobyte shared memory usage per thread block. So 2 thread blocks active at the same time. Again, 2048 threads. So that's good. However, if you have a GPU where the thread count is limited to this per SM, then the number of blocks per SM is reduced to 1, it says. Then I computed it wrong, sorry. Let's compute it again. Sorry, you have 1024, yeah. 1024 threads inside the block. Okay. And if you have that, you have like 50% place more that you could use on the SM. Okay. So each sync thread can reduce the number of active threads for a block. So more thread blocks can be advantageous also for that purpose. So the rest of this thing is about rectangular matrices. So I will give you the slides again, but I will not cover that part because it is simple. You just need to do the correct check, and I mean, you need to reach that solution. So as you see, the same computation, phase-based computation happens, but now you need to check that if you are out of bounds once you try to perform some partial dot product. So once you have these ifs, you are done for rectangular matrices. Okay, so it is now 20 past 4. Let's give a 5-minute break, and then let's start streams, and then we are done. So we will be here at 25 past 4. Hi. Okay, so the last thing that we will cover today is GPU streams. Let me find it here. Okay. So we will talk about pinned memory, unpinned memory, direct memory access, what it means for performance. And then we will learn how to overlap data transfers with computation, and that will be useful again for problems with complexity like n log n. Okay, so DMA is a hardware used by CUDA memcopy for better efficiency. So it frees CPU for other tasks. So this is a special unit for data transfer. So it is the hardware unit specialized to transfer a number of bytes requested by operating system between physical memory address space regions. And it uses system interconnect, typically PCI Express into their systems. So this is the CPI main memory, and this is the PCI Express, and this is the GPU card. So DMA transfers everything from here to here. So modern computers use virtual memory management. Again, this is a little bit out of scope, but let me briefly talk about it. So many virtual memory spaces mapped into a single physical memory. So what you have in your pointer, in fact, is not the actual physical address, but the virtual address space address, and it is translated to physical address. And when you go there, there's a chance that you will not be able to find the data that you are looking for because maybe it is swapped to the disk. So there's a page and maybe it's swapped to the disk and the page is reloaded. So it's a page filed and you get the data. So this allows you to use more memory than you have, in fact. So DMA uses physical addresses. So when CUDA memcopy copies an array, it's implemented as one of or more DMA transfers. The address is translated and page presence again is checked for entire source and destination regions at the beginning of each DMA transfer. And no address translation for the rest of same DMA transfer so that high efficiency can be achieved. So you first find the page and you bring it, okay? So the operating system could accidentally page out the data that's being read or written by a DMA and page in another virtual page into the same physical location. And you need to do checks to avoid these kind of things. You need to, there is a significant overhead for the memory copies, right? But if you be sure that all the pages are there when you access them, then these overheads are not necessary. In fact, you can go and get a bunch of region together and bring it to the GPU device, right? So that's possible if you know that all the memory items, all the items are already there. So that's what we call as pinned memory. So they are still virtual memory pages, but they are marked so that they cannot be paged out. Using pinned memory is good, then why don't we use it to the extreme? Because that removes the first purpose of virtual memory, right? You want to use more memory than you have, but if you forbid all the pages to be swapped, then you cannot do that. So that uses system resources, in fact. So this is also called page locked memory, locked pages, etc., etc. So CPU memory that serves as the source or destination of a DMA transfer must be allocated as pin memory. So the DMA used by CUDA memcopy requires that any source or destination in the host memory is allocated as pin memory. If a source or destination of a CUDA memcopy in the host memory is not allocated in pin memory, it needs to be first copied to a pin memory, then extra, which is extra overhead also. Then it will be brought to the GPU by the DMA. So CUDA memcopy is faster if the host memory source or destination is allocated in pin memory, since no extra copy is needed. So you need to be careful, especially when your data transfer overhead increases faster than the amount of computation gains, okay, computing time, execution time gains. You can reduce that by using pinned memory, by using other techniques like prefetching. So how do you allocate pinned memory? Then CUDA host alloc. This has 3 parameters: address of pointer to the allocated memory, it's like CUDA malloc; size of the allocated memory in bytes, it's like CUDA malloc. But the extra parameter is optional, but CUDA host alloc default for now. You can use it, and it allocates it on the host. So CUDA free host is again 1 parameter, like CUDA free. It's the pointer to the memory to be freed. So the rest is in fact the same. So you just need to pass the pointer to the CUDA mem copy, and it will be faster. So pinned memory is a limited resource. Oversubscription can have serious consequences. You cannot, I mean, don't do it. Don't use more pinned memory than you have memory. So it's the same. Instead of CUDA malloc, just use CUDA host alloc with the same 2 parameters and CUDA host alloc default, and then CUDA mem copy will be like 2 times faster. So CUDA streams then. So until now, we use CUDA mem copy. It serializes the data transfer and GPU computation for vector addition kernel. So what do? We do these operations serially: CUDA mem copy, computation, CUDA mem copy. This is device, host to device, and device to host. So input data, and output data. Okay, so but all these things are happening in sequentially. Okay, and we are using only one direction at a time. So I mean, we can either transfer the data from here to here and here to here, and we can do it at the same time. But as you see, we are only using one way. So some CUDA devices support device overlap. You can simultaneously execute a kernel while copying data between device and host memory. So that's possible. In fact, recent devices support that. So how can you make this better? Let's say. So this is vector addition. And suppose that I have a very huge vector. And instead of transferring everything at once, I decided to divide it into chunks again. Transfer first the first chunk of A and the first chunk of B. Then while performing the first computation, the computation for the first chunk, in fact, I can transfer the second chunk of A and the second chunk of B. Okay. Once I am done, when I am reading back the output for the first chunk, I can perform the computation for the second chunk. And in the meantime, I can transfer the input data for the third chunk. Okay, this is possible because this is device to host, and this is host to device, and this is computation. So I can do this kind of pipelining, in fact. But until now, we didn't learn anything to enable such a pipelining, right? So CUDA supports parallel execution of kernels and CUDA mem copy with streams. So each stream is a queue of operations. So there they will have the operations are kernel launches and CUDA mem copy calls, and the operations in different streams can go in parallel. So that's the beauty of them. So this is task parallelism. So requests made from the host code are put into first in, first out queues. Queues are read and processed asynchronously by the driver and the device. So the driver ensures that commands in a queue are processed in sequence, memory copies, and before kernel launch. And then it runs in a FIFO manner. So CUDA mem copy, kernel launch, device synchronization, CUDA mem copy. So all of them are processed in sequence in a single queue. Okay. To allow concurrent copying and kernel execution, you can use multiple queues. So there is also CUDA events that you have with which you can have advanced synchronization among these multiple streams. but we will not cover that today because we don't have time. So we will just go over simple stream usage, and that will be sufficient for many use cases, in fact. So suppose that you have these kernels, you have these streams, stream 0 and stream 1, and you inserted these operations to the queue: A0 memcopy, B0 memcopy, kernel 0, C0 memcopy, A1 memcopy, B1 memcopy, etc., etc. Okay, so this is for stream 0, this is stream 1. So whenever a memcopy operation appears here, it goes to the copy engine, and whenever a kernel operation appears here or here, it goes to the kernel engine. Okay, and that is what, in fact, you need to do simply. So let's go over this also. So you can use streams, as we saw, to learn to overlap data transfer with computation. So let's see. This is how you do it. So until now, we see the pictures. Until now, we saw boxes, queues, and this is how you create that queue. CUDA stream T is the object that you need to use, and that's the object name of the object and the name of the second stream. And you just say CUDA stream create, give the address of the object, and you are done. Okay, so you have two streams now. So these are the device memory pointers for stream 0. These are the device memory pointers for stream 1. So suppose that you already malloc them, your allocation is done. And what you can do is this, right? So you can run two things at once. You can submit these operations at once. So CUDA memcopy async, we didn't see that. CUDA memcopies are blocking, but now this is not blocking. Okay, so the thread goes here. CUDA memcopy async, the thread goes here. So we are inserting these to the queue. So stream 0, stream 0, stream 0, stream 0 means that we insert these 4 operations one after another without waiting each of them to be completed to the stream 0 queue. And we do the same for the stream 1 queue. Okay. And let me see. Yes. Okay. So in the previous GPUs, there are things that you need to be careful about, but in fact, for recent GPUs, it's not very limiting limiting bottleneck, in fact. So what happens is, let me see, yeah. So here, for instance, A0 is transferred, B0 is transferred, computation is happening. I cannot transfer this guy, by the way, yet, right? Because it is here and this is here still. And this guy here, C0, blocks A1 and B1 transfer because I cannot transfer it here, I cannot transfer it here, and I need to transfer this guy. So I can only do it here at this point, and I continue like that. So instead of putting the elements to the queues like that, let's do a different one. So let's first add the CUDA memcopies, the input ones, and after that, let's execute the kernels, and after that, let's get the outputs back. Now, it will look like this one, in fact, okay? So it will work better. So I have time for an example, okay? I thought I would be able to, but let's see. So let's use streams, okay. So this is really simple. I have 8 jobs. Each of these jobs are the same. In fact, the execution of a kernel on different arrays though. So as you see, I have one job which allocates 32 million integers, an array of 32 million integers. Then perform, so ignore the 0 here. It's not in fact necessary. Why do I have? So one block, 64 threads, And then this performs this operation on these 32 million operations, okay? You may guess that these numbers are small compared to the number of cores in our GPUs. So we are not utilizing GPUs with a single job, with a single task. And as you see, these are running one after another because this is non-blocking, but they are still waiting for them. So this guy waits for this guy. Sorry, this guy waits for this guy already. So these are being executed sequentially. So if you do this, and execute it, you will see that it is taking, in fact, we can do maybe even MV-Prof. See how much time is taken for each job. So 32 million operations, and this is square root is expensive than the others. Multiplication. But as you see, okay, 8 calls for the kernel. Each of them took 1.2 seconds. And in fact, most of the time went for the kernel. So yeah, so let's wait for like 9 seconds, 10 seconds. Okay, so yeah, 9 seconds. So out of that, around 8.97 seconds out of this 9.2 seconds is going for the kernel. Okay, good. So how can we make this faster? So let's submit multiple jobs to multiple queues. Then they should run in parallel on the GPU, right? And there's this guy here. The same code, the kernel is exactly the same, but instead of submitting one kernel to the default stream, as we did before, here. Okay. By the way, this 0 is here because I will need it in the next code. So the stream parameter is the fourth parameter, and this is the shared memory size. So you give the shared memory amount to be used. You can also give the shared memory amount to be used by defining the shared memory as external inside the kernel. Here we don't have a shared memory. The purpose is just that, I mean, it just needs to be there because I need to pass the fourth parameter as the stream parameter. So as you see here, I am not passing the fourth parameter, so it goes to the default stream. But here, I pass the stream. So for each iteration, I am using a different stream, which I created, which I declared here and created here. And that's all. So let's run it instead of the as you see, it didn't took 9 seconds this time. So although it says 9.66 seconds overall GPU work, the real time, the whole clock time is around 1.4 seconds, and 1.2 seconds of this goes for the kernel execution. Okay, so we are like a lot significantly faster because of this. So this is a very small number. We weren't utilizing the GPU, but if you have like small jobs, small tasks like that, you can still submit them to GPU by using multiple streams, and you will utilize your GPU. So that's the lesson from this thing. And one more thing is, again, a basic mistake people are doing. So here, as you see, I have a dummy kernel. It doesn't do anything. It gets 0 as the parameter. So since it gets 0 as the parameter, this for loop will not be executed. And it runs with a single thread, so it's not very compute intensive. But I just put it here to show you that once the rest is the same, by the way, as you see. Again, I am using different stream for each real kernel call, except the dummy kernel calls. Okay, so if you compile that, and run that, you will see that these things, although they are going to different queues, different streams, they still work one after another. Okay, as you see, again, 1.2 seconds per kernel call maximum, and this is the minimum one. Why this is minimum? Because this is the dummy call time, in fact. So this is the dummy call time. Again, this is 1 microsecond, 2 microseconds, so it doesn't mean anything compared to this 1.2 seconds. But it made these things, these large kernel calls, real kernel calls, sequential. Why? Because although these things are capable of being executed in parallel, asynchronously, they are still, they should be still synchronized with the default queue. Okay, so there is a default queue, there is a default stream, and once you put these dummy kernels inside, since the default queue in fact makes all these other streams synchronized, sequential, because you put one operation to the default queue after, and one operation from a stream. Okay, so don't do this. But even if you want to do this, and even maybe you have a code which is already using the default queue for synchronization purposes for some reason, and you have, for instance, this parameter default stream per thread. So if you do this, if you compile it, okay, so the same code, the same thing, then it will give you a better result again. Let me see, yeah. So again, 1.4 seconds, something like that, 1.2 seconds per kernel call, because what we said is the default stream is per thread. So per each thread, there is a default stream, but that stream is not the global default stream. In fact, it's an ordinary stream that, like the ones that we generated, but it's automatically created, automatically managed per thread, okay, per CPU thread. So if you have that, even if you have the dummy calls, the kernel executions is not sequential anymore. Okay. So I think we are done. And if you have any questions, please ask. There is a question from chat, I think. No, thank you. Thank you for listening. And I mean, in a single day, we could only cover that much, but I tried to cover as much as possible. And tomorrow's lectures will be more and more exciting, I believe. So please attend that also to complete this course. And again, if you have questions about CUDA programming, GPUs, how to use GPUs for your tasks, let me know. I will be able to help you, hopefully. So no other questions. Then I think we are done. Muslim
yes, we can end the webinar now. So thank you so much for your valuable training, and thank you all for the active participation in this event. We will continue tomorrow. So have a nice day.
Have a nice day.
Bye.
Bye.